Hello everyone, I'm your host Asma, and today we'll be exploring the false position method using Python. So, this numerical technique is designed to find the roots of a continuous function within a specified interval. Unlike some other root finding methods, it utilizes linear interpolation between 2 points on the function to iteratively refine the interval containing the root. So, by using Python, we'll delve into the implementation of the false position method, gaining practical insights into how it systematically refines its approximation with each iteration to converge towards the actual root of a given function. Now, here's its algorithm. As I've mentioned earlier, it is a technique for approximating the root of a given continuous function within a specified interval. The algorithm begins by checking that the function values at the interval endpoints have opposite signs, a prerequisite for the method. It then iteratively refines the interval based on the false position formula, computing a new approximation C as the weighted average of the endpoints. The method checks for convergence by examining the absolute value of the function at C, and if it falls below a predefined tolerance, the algorithm concludes. Throughout the iterations, the interval is updated to maintain opposite signs at the endpoints, facilitating the convergence towards the root. The process continues until either the root is found within the tolerance or the maximum number of iterations is reached. An example usage demonstrates how to apply the false position method to a specific target function, showcasing the approximate root and the number of iterations performed. If the method does not converge within the specified tolerance, a corresponding message is displayed. Now, in the provided code, the false position method is employed to estimate the root of a cubic polynomial function, which is fx is equals to x cubed minus 5x minus 9. The implementation resides in the false position function, where variables that are x0 and x1 represent user provided initial guesses for the root, and e denotes the specified tolerable error. Throughout the iterative refinement process within the function, variables like step keep track of the iteration number, and x2 represents the updated approximation of the root. The user is prompted to input initial guesses x0 and x1 and the tolerable error, that is e. Then it converts these inputs to floating point numbers, and a check is performed to ensure that the initial guesses appropriately bracket the root by examining the sign of the product of function values at the guesses. If the guesses are deemed unsuitable, the user is prompted to try again. And if the initial guesses bracket the root properly, the false position method is executed, providing iterative updates on the approximated root x2 and corresponding function values until convergence. The final approximate root is then displayed to the user, offering a practical introduction to the false position method and guiding users through the process of finding roots with iterative refinement based on function values at interval endpoints. Once we run this code, this is our output. We've given first guess, that is x0 as minus 2, and second guess, that is x1 as 3, with a tolerable error of 0.3. So then the output displays the results of each iteration. As you can see, there are a total of 3 iterations. The process converges to the final approximate root x2 is equals to 2.8466. The negative values of x2 indicates that the root lies to the left of x2, and the method successfully refines the interval approaching the actual root. So the final approximate root satisfies the tolerable error condition. This was all for today's video. Thank you for watching. I hope you found it helpful. I'll catch you guys in the next video.